Before we dive in, sort of want to talk about, the whole premise of the data lake. I actually spent a really long time at Teradata doing benchmarking and performance tuning. Back in, 2010, we started noticing that benchmarks started to dry up. Customers were saying, okay, well, hey, there's this cool new thing called Hadoop and this concept of a data lake. And I'm told that I can store not just the structured stuff that goes into the data warehouse, but I can also store, unstructured data, semi-structured data, JSON data. I can take all of this stuff and just kind of put it into my data lake and store it forever, right? Back in 2010, we didn't quite know what that meant. What are we going to do with this data later? Okay, well, ultimately the goal was we're going to do some data science and machine learning on it. But back then, the plan was, all right, let's take all our data, put it all in the data lake, and we'll figure out what to do with it later. The problem with this approach was that you ended up collecting a lot of garbage data. Right? You ended up with processes that would take data from your source systems, fail to kind of like clean things up and normalize things, dump everything into the data lake. So garbage in, garbage stored, and later, a few years down the line, data scientists started to go and look at this data and go, hey, let's actually do some machine learning on this. Wait, the data's junk. Half of this is corrupt. What happened? So does this actually resonate with some of you? Have you been through this journey of building a data lake and failed miserably? Kind of, sort of? So I mean, let's kind of dive into what that means, right? What does a typical data lake project looks like? So I actually used to also work for a mobile gaming company, so we can sort of use that as an example. Let's say you have a whole bunch of streaming data, event-based data. Maybe this is data that's from your cell phone, you're interacting with an application or with a game or something. You have a whole slew of event data that's coming into, say, like a streaming message bus like Kafka. And you decide, okay, well, what am I going to use to process this data? And you go, okay, I heard about this thing called Apache Spark. Has connectors to Kafka, has this thing called structured streaming. We can use this to do some streaming analytics. But what if I wanted to sort of reason about data that's older? Like streaming data is more about near real time, what's going on in the business right now today. What if I wanted to understand what happened last week or what happened a month ago? And so that's challenge number one. How do you do historical queries in this sort of an environment? You build out this thing called a Lambda architecture, right? And basically you have a speed layer and a batch layer. You have all this data coming into your speed layer, and periodically you take this data and you move it into a batch layer. You marry the two with a view on top or something, and then that way you can sort of have a view of what's going on in the business in the last hour, as well as let's persist all the data that we've gotten so far, write this out to data lake. And then, of course, you can also use Apache Spark to process data that's sitting out on the data lake if you wanted to do any reporting or BI, SQL analytics afterward. But that leads us to challenge number two. What happens when there's messy data? Like schemas change, file formats, or rather data is inconsistent. I've seen this over and over with customers. Is after they've started building this out, they go, "Hey, the data in my speed layer doesn't quite match batch layer. Something's going on here. How do I start enforcing like quality of the data that I'm actually looking at?" So you come up with a framework to start building like custom validation rules to try to make sure that your data is consistent. Right? Okay. So step one was to build a Lambda architecture. Step two, start building validation patterns to make sure your data is kind of consistent. But how about challenge number three? Turns out software can have bugs. So you might have upstream changes with your platform team. You might have upstream changes that kind of break your data. So how do I go and reprocess this stuff? How do I go and say, oh, platform team said they released a software update that caused a bug, and now we have a whole bunch of bad data. We got to reprocess last week's worth of this type of event data. How do I do that? So you come up with a scheme to go, okay, well, since Parquet and ORC and other Hadoop file formats are pretty much immutable, let's come up with a partitioning scheme. Let's say we partition our event data by date. And we'll just go and reprocess that data for that entire day or that entire week. Okay, but fine. We figured out a reprocessing framework. But what if you wanted to go and perform some updates to this data? What if you're doing like change data capture and you have to go and update data that's sitting out in your data lake? That's another thing that's not inherently supported in the big data Spark paradigm. So you have to come up with some more creative ways to do things like updates and merges, pretty much following that same pattern that you were doing with the whole partition replacement and whatnot. Since Spark or Hive didn't actually support transactions and ACID and the ability to do updates or deletes. But let's say you're running the DevOps team, you're the data engineers, you have downstream consumers. Like, when do I actually find time to do all this stuff, right? Because the system is not atomic, it's not isolated. There's no ACID, right? There's no ACID in a data lake. So if you make changes to your underlying data, it affects the downstream readers. And again, if something happens during the middle of job processing and a job fails, you might have inconsistent data that's written out. So you got to find time to do this, like on the weekend. I'm sure you've all been in a situation where you have to write an email that says, hey, yeah, system's not going to be available between 12 a.m. and 3 a.m. on Saturday morning because we're going to be doing some updates. So, I mean, ultimately, what this ends up being is you spend a whole lot of time and money just solving systems problems and not actually deriving value from any of your data. So, what does this mean? If you take a look at what actually happens in this model, there's no atomicity, right? So that means that, as I mentioned before, you have a production job that fails, right? And you've written out your table halfway. Or maybe it's written out some corrupt files and now all of a sudden your entire table is not readable. Okay, there's no quality enforcement, meaning if platform team decides to change the schema, introduce some new data types, introduce some new columns, and forgot to tell data engineering, then that might break some things downstream. No isolation or consistency, right? So there's no way to really conveniently to have multiple writers and readers appending to like the same table. You have to come up with things like the Lambda architecture and then ETL processes or Spark jobs that go and try to make things consistent. So this is kind of like, this is where the Delta Lake project comes in, okay? Basically, you take this architecture and you simplify it, you distill it down into something that looks like this. And so you can kind of see data movement from the left to the right. We call this a medallion model. So you can think of it as increasing incremental levels of data quality. And so you take source data on the left from Kafka or Kinesis or maybe even your existing data lake, and this is kind of the important point to make here. Delta Lake doesn't replace a data lake, it sits alongside it, it can consume from it. It basically gives you a layer on top that enforces quality and schema and all sorts of things, and we'll go into how that actually works. Let's start with what you typically see in the bronze layer, the raw ingestion layer. Right? This could be, let's say if you're consuming from Kafka, this could be a Kafka message that comes off with the schema of a Kafka message. So you have something like a topic or a partition ID, maybe the sequence that was last read, and the actual payload in maybe like a JSON blob. Same thing for Kinesis. Maybe if you're ingesting things directly from your data lake, this could just be, take your JSON data and we're going to convert it into Delta. And think of each one of these sections as like a SQL table almost. You're writing data to a raw table, and then you're moving data from raw into silver, and you're moving, your aggregated or clean data into gold for your business level reporting and aggregation. Silver would be that place where you basically take all of your raw data, you clean it up, you do your deduping, you make sure that your column names are normalized, the data types are correct. And this is kind of like the basis for all of your downstream aggregations and summaries and whatnot. If you ever want to come back and look at what the quote-unquote raw data looked like, but after it's been cleaned and normalized, this is where your organization would come in and say, okay, this is what the data looks like before I summarized it. And then of course, gold is typically what you would do in data warehousing land. You use summary tables, aggregations, what you open up for BI tools. Maybe you consume this using Spark SQL or even Presto. Questions before I continue going? The slides actually are available on the Scale website. Okay, so we talked a lot about moving data between these different levels of data quality, these different delta tables. How do you actually do that? So believe it or not, you can actually use structured streaming to move data between different Delta tables. Now you go, okay, wait, why am I using streaming? Isn't this more like a batch process? The cool thing about using Delta with Spark, especially with structured streaming, is that you can use the built-in things that make, you know, this processing much easier. Like, how do you keep track of what files have already been processed? How do you keep track of new records upstream? How do you automatically propagate those changes? And how do you ensure exactly one's semantics? Instead of having a streaming job that runs 24/7, you can actually set streaming jobs that say, hey, let's go and process all the data that I haven't processed since the last time I ran this job. You can create structured streaming jobs that say, hey, trigger once. Read everything in, write everything out to my next level, and then shut the job down. We'll schedule this to run once a day, once an hour. And then you can just kind of avoid the whole headache of, okay, how do I actually manage what's been processed and whatnot? And kind of obfuscates all that complexity out of like building pipelines that move data between your different levels of data quality. On top of that, because Delta Lake introduces the whole concept of ACID compliance to your data lake, you can now go and do things like updates and deletes and merges at different levels of your Delta tables. And we can actually, well, I'll actually walk through how Delta Lake works under the covers in a little bit so that you understand how you can actually do these things with immutable data formats like Parquet. I mean, this is especially important now that we have CCPA in California. So if you get a request for a DSR from a user, you can go in and say, okay, well, I'm going to go and delete all data with this user ID. Okay? And then finally, of course, because software isn't without bugs, it's really easy to use Delta to recompute tables. You can go in and say, I want to delete all of this stuff. I want to delete all of this event type, and I want to reprocess it. I want to restart my streams. And then you can start from your raw layer again, take all your data that's been persisted again forever, and then recalculate and recompute everything without really affecting any of your downstream users because you're doing everything using ACID transactions. So I want to quickly touch on some of the folks that are using Delta Lake today. We say this all the time and this never changes. There's been more than an exabyte of data that's been processed through Delta Lake in the last month. Some of the really popular ones that are here in Los Angeles that I work with personally are Jam City and Riot Games. Wanted to kind of zero in on a couple of the use cases. So Comcast is very interesting because it actually follows that bronze, silver, gold medallion model. Basically what they do is they collect a whole ton of data from those set-top remotes, which then goes through this process of cleaning and aggregating and filtering. And the end goal is basically to build machine learning models to improve their speech detection algorithms. They had this running on Spark without using Delta Lake, but they had to split this up into like 10 different Spark jobs, following that whole crazy Lambda architecture and whatnot. They took like one query and they had to partition it out across 10 different clusters, but they switched to Delta, and they were able to reduce the compute capacity or the power that they needed to run these jobs from 640 instances on EC2 running on AWS down to 64. Basically, all that time not spent managing these extra jobs is time they can now spend innovating. Sam's Club is another really interesting use case. They do everything with Spark, including like finance to forecast sales and wages, assortment, so that's stuff like how do we decide what items to physically sell on the finite amount of shelf space that I have in a store. They have sales tools that help them determine how much to produce on a given day for fresh items like rotisserie chicken or fresh meat, or how many muffins to bake. You don't want to make too much, or you don't want to make too little. And of course, your standard gamut of fraud engines and personalization and recommendation systems. The goal for them was basically to migrate from an on-prem system into the cloud, because the cloud is the future for them. And they used Airflow to orchestrate a job that takes data from Teradata on-premise into Swift object storage, which then triggered additional jobs that moved this into Azure Blob Storage, and then into multiple Databricks workspaces in running in Azure. Super easy with Delta because it's really easy to create tables and update them and delete things. Basically, before Delta, they were trying to build this in-house solution that did that whole partition swapping shenanigans that I tried to explain earlier. But because we have transactional updates with Delta, this greatly simplified their pipelines. They actually had queries that did basic aggregations that, like figure out retail sales over the period of 1 year. This improved from before Delta running over an hour down to less than 6 seconds with Delta. And just to kind of give you an idea, that same type of query ran on their Teradata system and it took 30 seconds to execute. So how do we actually get started using Delta Lake? It's actually quite simple. It's been published as a Spark package, so you can say, PySpark -- packages and then include the version of Delta Lake. You can use Spark Shell with the same -- packages. You can include Maven dependencies, add things to your SBT build file and to your pom.xml, and include Delta Lake into your projects. And to get started, it's actually, think of Delta Lake like a file format. So instead of saying dataframe.write.format Parquet, say dataframe.write.format Delta. That's pretty much all you have to do to get started. One thing I did wanted to bring up that's in progress now is a new feature called declarative pipelines. Basically, this allows you to enforce, not just necessarily things like schema, but end-to-end, like, okay, where's my query, where's my data coming from, right? Where are we storing this data? What should the schema look like exactly? If you're using a Hive metastore, what should the table DDL look like? What's the description for the data that's coming in? You can tag all of this data as it's coming in, and then you can additionally start setting expectations on data quality. So sure, you can do schema enforcement, you can do data type checking, but how do you do invariant checking? Like, what if I want to know that data that I'm getting is in a certain range value, or the data that I'm getting is not from 1969 because there is some problem upstream? And then once we figure that out, what do we want to do with that data? Do I want to fail my pipelines? Probably not, because you get a lot of bad data in production pipelines, and you have jobs that are just failing every 10 minutes. Maybe you want to set a threshold for alerting. So maybe if 10% of my data is bad, I want to send an alert. I want to let somebody know that, hey, we're getting more data that's bad than usual. Or maybe I want to just go ahead and quarantine that data into another table so I can go and take a look at it later. All of these things are things that are going to be supported in declarative pipelines. That's probably going to be available in the next couple of quarters with the release of Spark 3.0. Okay, questions before we dive into actually like how Delta Lake works under the covers and what you might see when you take a look at the internals of a Delta Lake table? Is everybody just completely lost, or is this making sense?
I had a
Okay,
question.
just checking.
I had a quick question. You said that Sam's Club had a query that in Teradata took them 30 seconds.
Yes.
They moved to Spark. It took them over an hour.
Yes.
And then they moved, and then got to, why did they move to Spark if it took them over an hour in the first place?
Well, so Teradata was on-premise. They were trying to build these systems in the cloud, and they were trying to see if, do we need a cloud data warehouse, or can we run everything with Spark? So initially, they tried using Spark, and they said, oh, this kind of sucks. And then we said, use Delta. And then, it was a problem of optimizing on I/O. And Delta, I can explain that later. Delta helps you basically rapidly eliminate the amount of I/O that you have to do so that your queries run faster. Great question. Okay, so how does Delta Lake work under the covers? So if you take a look at Delta, right? Basically, Delta tables, just like Parquet tables or ORC, get written out to disk, right? And this is kind of like the file tree of what a typical Delta table looks like. So you have a transaction log. This is how we achieve ACID compliance. Inside that transaction log, there are different table versions. These are JSON files that represent what happens or what happened inside that specific version to create that version of the table. And of course, there's options to still use partitioning like you would in Hive or in Spark SQL, But we say this is optional because Delta actually has some tricks so that you may not necessarily need to partition your data to get optimal I/O elimination. You can kind of reason about what a Delta table is just by thinking about it as a set of actions. So let's say you have, we had those different versions of the table in the transaction log, and you had information about what happened, what changes happened to my data to create that version of the table. So that could have been a change in metadata. That could have been, okay, I renamed this column. I changed the schema a little bit by adding columns or removing columns. I changed the partitioning scheme. So a change in metadata. And ultimately, when you append data to a table, you're adding files, right? If you're updating or deleting, you're essentially adding new versions of a file and then marking old ones for removal or deletion. So ultimately, a transaction log shows the current metadata, the list of files that belong to that snapshot of the table, along with like a list of transactions and versions and whatnot. So you can think of the changes to the table as atomic units called commits. So in version 0, we added these two Parquet files because we appended this data. Okay, and then in version 1, we updated something, or we deleted a user ID or something. So we needed to restate Parquet files 1 and 2, and we created another version, Parquet 3. So when we go and query that table, we see that, oh, in version 1, we only need to read 3.parquet. Okay? And then you have to make sure that if there are multiple users, multiple writers, multiple readers acting on this table, that there is some level of consistency. So let's say you had user 1, and user 1 created version 0 of the table. So they did the create table, and they inserted some data into it. Then user 2 went and added some data to that table. Delta should know that if user 1 and 2 try to modify the table again, that they can't both create a version 2, right? If user 2 created version 2 first, then user 1 should create a version 3. So this kind of leads into the next discussion of how Delta solves the whole, concurrency issue. Like what actually happens if two writers try to update a table at the same time? So what happens is, two users are trying to make a change to this table. They both see that there's version 0 of this table, so they both record a start version. And then the job starts, right? And then you go within the jobs that are running, you say, okay, well, I'm going to do something like, I'm going to read the schema, and I'm just going to append some data to this table. And they're both doing this, and let's say this is like 2 different streaming jobs that are writing to this table, right? And then as soon as that batch is complete, if somebody goes to attempt to commit some data, the first person there will win. So user 1 in this case created version 1 of the table, and then user 2 goes and tries to run version 1 and says, hey, wait a minute, table changed. So we should actually check to see if there were any changes that might have affected what I read. Since in this specific example, we only read the schema and we were appending data, we weren't updating, we can be confident that none of the underlying data changed. So then user 2 automatically goes and creates a version 2 of the table. So in database world, typically you do locking, right? Like if you're trying to update a table, the writer locks the table and everyone else has to wait for that lock. It's more like a pessimistic concurrency model. In Delta Lake, we'll both assume that I'm the only one writing to this table, but I'm going to check again before I commit that data to see if there have been any changes. And if the changes did not affect what I read, then I'm just going to go ahead and append as the next version of the table. If there was an update and it affected what I read, then recompute.
Why? Like, why wouldn't you keep the pessimistic locking thing? Like, especially if your company's data depends on this, why would you allow people to potentially screw this up?
Where would you manage? So because it's a distributed system and you're using multiple clusters, your writers don't necessarily just exist in one system, right? So in a database, everything's happening, everything's managed by one database. In the decoupled compute from storage world where you have data out on S3 or on Azure Blob and you have multiple different systems and clusters trying to access this data, who is managing the central locking? That's why.
So then somebody has to also manage the who wins, right?
Right, but that is managed by the individual clusters that are doing the writes, right? Because right before, let's say user 1 and 2 are committing data, user 1 finishes first, user 2 doesn't know that, right? It only goes to check to see if this was committed before it tries to write. So there's a central transaction log that's sitting out on blob storage. And then each of the readers and writers are responsible for checking the transaction log to make sure there have been no changes. There's no central system that says, hey, you can't do this because this has changed. It's, I'm going to see if I can do this before I try to do it. Does that make sense?
It sounds like you're moving the lock to after the transaction instead of before. And you're still using a centralized determinant of whether or not who wins and who loses.
Sure, but nobody is actively managing locks.
Okay.
So I think the confusion is this is a form of optimistic locking, right?
Yes.
Academic papers, and typically you have two different writers writing different rows, and they're allowed to, and then
I'm going to give this to you because we need to hear it for the recording.
So if I remember correctly, this is a form of optimistic locking. It's written about in academic papers, but normally it's discussed in terms of row-level transactions. And so compared to the pessimistic locking, if you're locking at the rows instead of the tables, that's a lot of overhead. So the idea is to reduce the overhead at that, at that level and do one check at the end. I believe, fuzzy on my memory there, but I think that was the idea.
Awesome, thank you. Cool. And then one more thing I wanted to point out. You have to think that, okay, you have all of this data that's sitting in these transaction logs. What if I have tables that have millions and millions and millions of files? Like how do we handle these JSON files that have all of these entries? And the answer is we actually use Spark for that, right? So you have these JSON files that say, hey, in version 1 and version 2, I added these files. In version 3, I removed these files. What Spark will do is periodically take all of this information and then distill these things down into checkpoint files in Parquet. So you'll notice that if you're running queries against the Delta table, there's actually another Spark job that goes and runs and parses and figures out, hey, let's cancel out the files that don't exist for this snapshot of the table and then figure out what I can read. So let's touch on roadmap real quick, and then I'll jump into a demo environment. We can actually go and run some code and see how this works. So, Delta Lake has come a long way since it was announced at Spark Summit in April. We initially added support for S3 and ADLS. Initially, it only supported HDFS. We added, update, delete, and merge APIs for Scala and Python. We also added vacuum for Scala, so you got to think that if you have an update that runs or a delete that runs, and now you have files that are deleted, they still exist on S3, and so now you have to vacuum them. Like same concept of cleaning stuff up in like PostgreSQL or something, running a vacuum command. We also introduced convert to Delta, which means you can take existing Parquet data and then create a Delta table without having to create a new version or copy data or restate anything. And then, in version 5, which was actually introduced in December, we introduced Presto manifest. So now you can use Presto or Athena to actually query a Delta table, whereas historically you needed a Spark-based system that could interpret how to read the Delta transaction log. And then after Spark 3.0 is released for open source Delta Lake, we'll have support for DDL, so you can do create table and then have that managed by the Hive metastore. Right now, metadata for a Delta table is managed by the transaction log, so schema information, column information, all of that is stored in the transaction log and not in a Hive metastore like it is for Parquet tables. And then there will be SQL-based DML support. Right now, if you wanted to do updates or merges, you have to use DataFrames APIs. But you will be able to use SQL to just say update table, set something or other, or merge into table, and then your conditions. Okay.
Quick question on this. Is
Yes.
So earlier in Spark's history, Python was always a second-class citizen, and then it became elevated to a more first-class citizen. Is Scala still the first-class citizen, or would you say that Python's performance is comparable?
Performance is identical. There are a couple of scenarios where Python might not not be my first choice, not necessarily for Delta, but just for Spark in general. The most notable one is with UDFs. Right, if you're creating SQL UDFs and if you create SQL UDFs in Python, you have to serialize data in and out of Python process that's running on every executor, whereas if you wrote your UDF in Scala, that wouldn't be the case. Okay, if you want to get started with Delta Lake, it's an open source project. It's available at delta.io. That's where all of our documentation is, links to the GitHub repository, announcements about new features that are coming. So definitely check this out if you're interested. So the next part of the presentation is going to be more like an interactive demo. So again, if you want to follow along, let me actually start mirroring my screen. All right. There we go. Okay, so if you want to follow along, you can sign up for, I'm going to do this, this demonstration in Databricks. It's a quick and easy way to get started with a Spark environment. So if you'd like to follow along, you can sign up for the Databricks Community Edition. That's just at databricks.com. Try Databricks. Make sure you click on the Community Edition and not Free Trial. Free Trial requires you to put credit card information in. I mean, you can if you want, but it'll start billing you after 2 weeks. So Community Edition is what you want to do. Okay. So let's do like a quick run through of how I would interact with Delta Lake in Spark. So let's say this is the scenario. I can share this notebook afterward, and I don't know if there's a public place on the website where I can say, hey, this is the notebook that we used, or
I'll have to talk to Alon about that, but I don't think it'll be too much of an issue to just drop a notebook up there.
Okay, cool. So let's take a look at how to get started. So what I'm going to do here is set up some code paths. This is actually all writing out to blob storage. And then we're going to set some Spark parameters to make this configuration more friendly to run on a tiny cluster. Okay, so how do we do this with Parquet? Create a data frame, and we're just going to make up some data, right? So we're going to create 100,000 rows, and then we're going to split that into, let's think of this as like IoT data, right? So let's say it's like a door sensor or a door lock or something. There are actions like open and close, and then we're going to make up a timestamp for when this data was created. And so let's just go ahead and define that as raw data frame, okay? And then write this data out to Parquet. That's your typical run-of-the-mill data frame.write.format Parquet. We're going to partition this by date, and then we're going to save it in that path that we defined earlier. I'm happy to pause if people are actually signing up for the Community Edition and they want me to wait.
I'm signing up right now, but I'll...
Okay. All right, sounds good. So, dataframe.write.format Parquet, and then let's just go ahead and quickly read that back in and see what the data that we generated looked like. So, I mean, it's super, super interesting data, right? It's open and closed with some fake device IDs and a date that this stuff was recorded. Okay, cool. I mean, what are some of the things that we can do with this data? We can do some simple aggregations, right? Let's say I want to do a data frame group by and count how many different actions there are. Not surprisingly, there's 50,000 of each because that's how we created the data frame. So what if I wanted to append some data to this table? So let's say that I'm going to create a read stream, and I'm going to start generating some new open actions. Okay, and I'm just going to generate some fake dates for this. And I'm going to start writing this out to the same path. All right, so this is just pretty basic streaming data frame write. We're running this every 5 seconds and writing this out to that same table that we created earlier. So let's make sure that this is actually processing some data before we move forward. Okay, there we go. So every 5 seconds, we're going to start writing out hundreds of records. Okay, let's do another count on this Parquet data. Okay, we've had several batches of this being written. And then you go, well, okay, hang on, wait a minute. Earlier, we had 50,000 open actions and 50,000 close actions, and we were appending data, right? What happened? What happened to our counts? The problem with this is Spark's file sync implementation doesn't actually support batch and streaming. So you can't have a batch-based table and stream to it at the same time. It messes things up. This kind of goes back to that whole, got to have a Lambda architecture and got to have a streaming table and a batch table, otherwise things get messed up. So what if you were to do this with Delta Lake? We're going to do the same thing. We're going to take our raw data. We're going to write it out to Delta this time, and the only thing we've changed is the file format name. Still partitioning by date. Okay, and then we're going to be able to do the same group by aggregation so that we can see that we'll have 50,000 of each action. I should stop spoiling this and let you just see it after it runs. Okay, and then we'll do the same thing, right? We'll create another streaming data frame, and then we're going to write to Delta. We're starting to generate more of the open events again. So let's wait for the stream to initialize and start writing some records. Okay, there we go. I'm going to let this run for a few batches so that we can actually see some interesting data being written out. Okay, and then let's go ahead and do a count. So we got some records that have been written. This is not very surprising. This is going to work. Spoiler alert. The other thing I'm not supposed to be doing is running these things live because you never know what's going to happen. But I like to live dangerously. But anyway, there we go. I wasn't lying. Now you can see the additional records that we're adding are actually showing up. And now we're streaming into a table that we've been doing batch operations into. Okay. Let's talk about using Delta Lake as a source, because we talked about the different medallion levels of bronze, silver, gold, and moving data in between. So what does that sort of look like? You can use Delta Lake as a source. And so instead of just using Kafka or something, you can say, oh, let's do a read stream from this Delta table. Okay, and then you can use that to, let's say you're moving from like silver into gold, and so you wanted to do a basic aggregation that counted all the different actions and dates and device IDs. Okay, so define a simple read stream with your Delta tables as the source, and then take that data frame, do your typical standard Spark data frame aggregations, and then write that back out to what you now consider your next level of aggregation or your gold version of your Delta table. Go ahead and let that process a few records. And let's see if we've gotten anything yet. Any questions while this is running and combat the awkward silence? Cool. Okay, so we've got some records written out to our gold path now. If we run this query again, you'll see like additional data that's been written to this table. There we go. All right, let me go ahead and cancel this. All right, so let's talk about schema evolution. We talked about what do we do if the upstream data source changes their schema and forgets to tell us. You notice that, okay, let's say I was a platform team and I introduced a user ID to this schema and I forgot to tell data engineering. Delta will actually fail that job and say, hey, wait a minute, we've detected a schema change upstream. Did you mean to do this? So this kind of goes back to the whole garbage in, garbage out thing. If you try to build your data lake to be too permissive, then you end up with unexpected changes. And so you can actually have Delta automatically support schema evolution, but by default, the jobs will stop and say, hey, there's been a schema mismatch. If you want schema evolution to be automatically supported, you actually just create the right stream with an option called merge schema equals true. And then it will allow you to write the schema changes. And then when you take a look at Delta table, you'll see, okay, well, in my latest version of the Delta table, there's a new column called user ID. But previously there wasn't, and that's kind of where the whole time travel thing comes in. So time travel is kind of like a happy consequence of the whole data snapshot transaction log model. I told you that there were increasing versions of this table. So there's version 0, then we added some files, there's version 1, we added some more files, we made a schema change, there's version 2. So let's take a look. This particular table has 19 different versions because every iteration of like a streaming query was a new version of the table. I know that I probably made a schema change before version 2. I actually don't know that now, but it's a wild guess. And so let's take a look at what the table looks like right now. And rather, it'd probably be better if we just did a count of how many records that we had in the Delta table right now. I should also stop these streams so that I stop adding more data to this. Cancel that. And I'm going to cancel that. All right, so table looks like this. Right now, there's a user ID column now that we added. And total number of records, 130,000. But what if we wanted to see, what did the table look like before we made that schema change? So I can actually query this table by using version as of. And say, you can see for version 2 of this table, there was no user ID. And likewise, if you wanted to see the count of records that was in version 2, same thing, version as of 2, it was only 100,000 records in here instead of 130. So Delta Lake allows you to travel back in time, so to speak. This becomes immensely important, not necessarily, as a data engineer, if you submit an update or a delete and forget to specify the appropriate predicates. But if you were doing something like machine learning and you wanted to, all machine learning it's important for you to understand exactly what versions of the data you actually use to train your model. So you can actually set up things like MLflow to point to exactly what version of this data set at this table at what point in time that I use to train this model so that you can have reproducible experiments.
Can you check to see, I need to know, there was a version change 2 months ago, but I need the data in the intervening 2 months in that particular version that it was in 2 months ago, or is that not available?
Come again?
So let's suppose somebody admits we added the user ID field 2 months ago.
Uh-huh.
I need the other 3 fields for data today, up to today, for the intervening 2 months. How do I get at that?
So you added the user ID 2 months ago.
Yeah. And so if I could put it in, as you said, to use MLflow, I would just keep pointing to the table and just say I want data from in this version.
Right.
Just give me the data in that version, regardless of whatever happens later. That will work.
Right.
Okay.
Exactly. It's exactly that version. Not any data that's been appended to since, but the snapshot of the table from that point in time.
Is this enforced by a schema registry, or how is this enforcement?
So that's in the transaction log. So let me show you something. And this is something describe history as a SQL command that we just introduced in open source. Let's see, Delta Silverpath. Where was Delta Silverpath? Here we go. So this is the actual location of where I've written this data out. So if I wanted to see the history of this entire table, I can just do delta.path. Then you can see I wanted, 2 months ago, maybe you have the timestamp for 2 months ago, or you have the version number from 2 months ago. And these are the changes that were made. Like if you actually went and queried version 13 or queried timestamp as of this timestamp range, then you'll have the table as it was at that point in time. with all of the columns and the schema and whatnot, but nothing afterward.
Does this in any way communicate with, like, if I have a Kafka producer and the Kafka producer is using an Avro schema registry, does this in any way communicate with that?
No.
Okay. So you'd have two different schema enforcements in your streaming topology, right? One from Kafka, one for Spark, and they
Right.
don't necessarily talk to each other.
Right, exactly.
Okay.
Okay.
And what was the error you got?
Ah, this was the schema mismatch.
So just in case you guys are curious, we're recording, so in order to make sure that we hear, like, either let me give you the mic, or if he has to repeat the question.
And the question was, what was the error that was on screen?
Schema mismatch, the schema mismatch. Okay. Questions? Who signed up for Community Edition and wants to start messing around with some data sets? Really simple. You signed it. Are you on it? Okay. I can show you some really basic things just from like a vanilla notebook. You'll have access to something called Databricks datasets. So take a look at what's in there by doing like a %fs ls and then Databricks datasets. It'll show you all the public datasets that are available for you to manipulate in that Spark environment. And then the specific demo that we did today, we generated the dataset, but something very similar is available under Databricks datasets / structured streaming / events, I believe. Let's see how right I was. Okay, so these are all the data sets that are available to you that are public. And then these are the events that these look like the events that we did in the demo today. So if you just did a head on this file, looks a lot like the stuff that we generated. And then just to read this in, data frame equals spark.read.json, and then the path again was Databricks datasets / structured streaming / events. And then you can do a display data frame, and then you'll see the same type of data that we had earlier.
I know this is a really basic question, but you can export to a CSV and then download the file.
Yeah, absolutely. So you can, right here, download preview or download full results. But is there any reason why you would want to export data out of a distributed system into a CSV so that you have it in a non-distributed system?
Oh, no, just easier to view the data and manipulate it.
Okay, got it. All right, questions about anything that we talked about today, how to get started with Delta, how you might be using it in your environments?
Can you go back up to the ls command? How do we show the?
Oh, yeah. And this is unique to Databricks. So if you did a %fs, that's a magic command for file system, and then you did an ls, and then you pass in a path like Databricks datasets, then it'll give you, what's sitting out on Databricks file system. Okay, questions? Hopefully this was somewhat helpful or interesting. Please let me know. I'm really easy to reach. I'm just Steven@databricks.com, Steven with a V. If you have any questions about Delta Lake or Spark in general, please feel free to reach out.